Okay, so we will be talking about number of things in things, but actually I will be talking about number of things in graphs. We can definitely make many of these things also work for things in things, but like let's settle down to graphs. Okay, so one important question: why bound the number of things? Okay, so we bound the number of things because A, it gives us good algorithms, and B, it is fun. Okay, so now let me give you some of the combinatorial questions that we'll be considering in today's talk. So first thing is the first object that we will consider is called independent sets or stable sets. Okay, so I'm sure all of you have been hearing lots of pure maths talk. So this talk will be slightly different from your pure maths talk from. So I will be talking about combinatorics and counting and graph theory kind of things. So what are the independent sets? So it is a subset of vertex set. It's called independent if no edges between vertices in S. So for example, one question. So for example, look at this graph, right? There are no edges in this graph, right? So what is edge? Basically, this is called an edge. Okay. So when you do not have such things, then you call okay. So now the question which I'm interested in, what is the largest number of different independent sets a graph can have? So now look at this. There are no edges on this n vertex graph. So how many independent sets it can have? 2 power n, right? All subsets of this is an independent set because there are no edges. But you might say that it's cheating because maybe you can make the graph connected, but that will not change a lot because I can just make one vertex and connect it to every other vertex. Now notice that here I still have n-1 vertex and any subset of that is an independent set. Okay, so in this graph on n vertices, we definitely have at least 2 to the power n-1 independent sets, right? So it's like if I started with an n vertex graph, anyway, all number of subsets are like roughly 2 power n, like all subsets, like summation n choose I is like 2 power n, right? So this doesn't sound anything interesting, right? So what is an interesting question would be is that, can I prove something non-trivial about number of such independent sets? Okay, so I will come. So it means just asking for independent set was not a right question. But what about maximal independent set? So what is the meaning of maximal independent set? A vertex set is a maximal independent set if it is A, it is independent, and B, no proper superset is independent. So you cannot find a set of vertices, for example, right? So I'm going to call that this is a maximal independent set. But if you look at any subset of this, that is not maximal independent set, because if I give you these two, then you can add one more vertex from here without, like you can find a proper superset which is still independent. So when you say a maximal independent set, maximal means a set of vertices, right, such that it is independent. And if I add any other vertex to that set, it creates an edge. Okay, so those kind of sets are called maximal independent set. Okay, so if you have any questions at any point of time, please feel free to interrupt and ask question. So is the definition fine with all of you people? Okay, so now one can define maximal, minimal x in this way. So what is a minimal something? When you say minimal, meaning if I look at any subset of that, that does not have the property. Okay, so this is how you define maximal sum objects or minimal sum objects, by saying that, oh, it's a set of vertices such that I cannot extend it further, or it's a set of vertices, if I remove anything, it loses that property. So this is how you define maximal independent sets or minimal vertex cover or whatever. Now a natural question that we will be interested in, how many maximal independent set a graph has? Okay, so there exists a graph with 3 to the power n by 3 maximal independent sets. Okay, so here is disjoint triangles. Just one thing. Sorry, there was like my son was crying, so we had to settle him down. Okay, so there exists a graph with 3 to the power n by 3 maximal independent set. And why is that? Let's see. Okay, so now notice I have how many triangles? I have n by 3 triangles. Now, any maximal independent set will contain at most one vertex from each of this triangle, right? You can't contain more than one vertex, and every maximal independent set must contain at least one vertex from each of this triangle, which implies that you have 3 choices for the first one, 3 choices for the second one, and hence it is 3 to the power n by 3, right? And in 1965, Moon and Moser showed that actually this is all that you can have. This is the no graphs has more than 3 to the power n by 3, more than this many number of maximal independent sets, right? So now you, okay, so this is what we are going to show next, is that any graph contains at most 3 to the power n by 3 number of maximal independent sets. Okay. So our things here is maximal independent set, and in thing is our graph. Okay. And okay. So what is 3 to the power 1 by 3? It is a maximizing x to the power 1 by x over naturals. So if you maximize this over reals, this is like x will be like e, right? So, and then you know that either it will be 2 or 3, then you see that it is 3. Okay. So this is a number, and how will it come? You will see in a minute. And now give me a proof that number of maximal independent sets in a graph is this much. So let MIS be G, be a number which is the number of maximal independent sets in G. But what I'll be interested in, I want to say that any graph on n vertices contain at most these many maximal independent sets. So MI of S of n is max over all graphs on at most n vertices and number of maximal independent set that graph contains. So this is what we are interested in. Okay. Here's a very simple observation. Look at any graph and look at any vertex and its neighborhood. Okay. This is his neighborhood, meaning all the vertices which has an edge from V, right, are called neighborhood. And what is the closed neighborhood? You also include V. Now notice that we have a very beautiful observation that every maximal independent set in graph contains at least one vertex from the closed neighborhood of V. Why? Because if you did not contain any of these vertices, what happens? Then you look at any maximal independent set, look at any independent set that do not contain this. You could add V to this graph, right? V to that set, still maintaining the property that it is independent, which means that every maximal independent set has a property that it must contain at least one vertex from the closed neighborhood of vertex V. And it has nothing to do about one particular vertex, but this is the property of any vertex, right? So every MIS in G contains at least one vertex from closed neighborhood of every vertex, because if it avoids a closed neighborhood of some vertex, then we could add that vertex and increase its size contradicting the fact that what we started with is a maximal independent set. Okay, so having set out this plan, set out this property, we will see how this leads. Okay, so I'm going to ask how many maximal independent set in G containing V is equal to, like, so if I ask you how many maximal independent sets are there that contains V. So if you contains V, you cannot contain closed neighborhood of V. So you delete it, and in the rest of the graph, you find maximal independent sets. And in all those, you will add V to that, which implies that the MIS in G that contains V is equal to this number. Now, so every MIS in G contains at least one vertex from N of V. It means if I sum them over every U in closed neighborhood of V, and I sum them, so here it is, right? Okay, so look at any MIS. Either it is going to contain this vertex, or this vertex, or this vertex, or this vertex, or this vertex. So if I sum the MIS containing this vertex, sum these things, then I definitely get an upper bound on maximal independent sets of my graph. And that is what this summation is trying to represent. Just 1 second, I think. My internet is a bit slow here, so let me check. Hopefully it will move fast now. Okay, so this is what we, up until now, we agreed on. Okay, so what is the meaning of okay? So now look at this, right? So what is MIS of N, right? It is at most, if you look at a vertex of degree D, right? So how many, what is the size of its closed neighborhood is D plus 1. So in the recursive step, you are looking for your upper bound. How many problems are you creating? Look at this. So you have D plus 1 set. For each of them, you are creating one problem or one. So it is D plus 1 times. And what is the set of vertices you have removed is MIS N minus D plus 1. So this is basically N minus D plus 1, which is N. Okay. Okay. Now, this statement is true about any degree vertex. So in particular, this statement is true about if D I select is a minimum degree in G, such that, okay, in G. Okay. So let's select the minimum degree of my graph. So now what are we getting then? So by induction hypothesis, MIS of N is max over D greater than or equal to 0. This, because minimum degree could be anything in my graph. Okay. Now, suppose by induction hypothesis, I say that this is what MIS of this is this much, then you can 3 to the power n by 3 will come out and you have this number, and this is less than or equal to 1. So you can show that the maximal independent set in any graph is upper bounded by 3 to the power n by 3. Okay. So, or there are, if you do not want to do induction, then directly you can show also by just solving this recurrence, right? What is this recurrence is going to be? It is going to be D plus 1 to the power n by D plus 1, right? So basically we're trying to optimize this function, right? And that is what I said, it is x to the power 1 by x. So if you do this properly, you will get the 3 is the right number for this. Okay, so bounds versus in. So one thing is that, you know, like so many, only that many objects are there in my graph. So that is a bound. Okay, so, but another question which people are interested in is that, can I enumerate these structures, right? So there are different kind of questions people ask. Can I enumerate these structures one after another, and the time taken between them or the duration between them is polynomial? Or we can say, look, I don't know how many objects this particular graph had, but you enumerate it in a way is that it is upper bounded by the total size of this. Maybe the time taken between you give me one object and the other object is exponential. Okay, so people ask all kind of questions, but ultimately your objective is to compute these things, objects, or to enumerate these objects in time proportional to the number of objects in the graph, or the upper bound what you're able to prove, at least one of these three things. Okay, and generally look at this. I wrote a recurrence, right? Recurrence means that I can also just write a recursive algorithm, right? Do this, just put that into algorithm. Any recursive definition that you write, you can put it in an algorithm, and that will give you enumeration algorithm to enumerate, but just in the time proportional to the what we were able to prove now. Not, it is not, what is that called? Let's say, it is not sensitive to how many objects that particular graph is. It is only sensitive to upper bounds we are able to prove. Okay, but those are fine details. If you have interest, we can talk about this offline. Okay, so it has connection to what is called exponential time or branching algorithms. Okay, so basically you make this inductive proof into a running time analysis. And what is our goal? Our goal always is to beat the following kind of recurrence, right? T of n is at most 2 power t n minus 1. Why? Because what does this recurrence correspond to? You have any vertex, for example, or any of either this object is there or this object is not there. If this object is there, you delete it or do something, so that leads to this recurrence. Or if this object is not there, you delete it and the remaining graph on n. So, but what will this solve to? This is exactly same as trying all possible subsets, because this will solve to 2 power n. So number of subsets containing some element is how much? Number of subsets is you fix an element, either it is there or it is not there, right? So if it is there, in the remaining you find subsets not containing him. So that is T of n minus 1 plus this. So this is exactly what that recurrence corresponds to. Okay, and there are lots of good algorithmic applications. So for example, if I give you input graph G and ask you, does G have a proper 3 coloring? So what is a proper 3 coloring of a graph? It's basically you have a graph, okay, and your objective is to color your graph nodes or vertices with 3 colors, say 1, 2, and 3, or red, blue, green, whatever, such that every edge has the following property, that no endpoint of that edge has red, red, blue, blue, or green, green. That is, every edge is non-monochromatic, or otherwise every, like for every edge, endpoints get different colors. So my objective is, can I color the vertices of my graph with 3 colors so that no edge gets no endpoint of no edge gets the same color. Okay, so this is a 3 coloring problem, and it is known to be hard in the sense that you cannot solve this problem in these kind of running time, or rather polynomial time. Okay, so but what best can we hope for? Okay, so it's, and naively if you try to do, then you will try all 3 to the power n coloring, because every vertex could get either 1, 2, or 3. So there are n nodes. So it is 3 to the power n time algorithm, which is very naive algorithm. Okay. But what we can do, okay, what we can do actually is that using the bound on maximal independent set, we can come up with an algorithm that runs in this time. Okay, so it's an exercise, but if you notice, what you can say that, look, I enumerate one maximal independent set, and then remaining, I check whether graph is 2 colorable or not. And this objective to test whether graph is 2 colorable or not is p time. So for 2 colorability, what you will do, you start with a node, you say, okay, he needs to be assigned some color, red or blue. So let him assign red. If he's assigned red, what are all his neighbors needs to be assigned? Blue. And you propagate this. If you are able to succeed in this propagation, then you will get a proper 2 coloring. Okay. So this is why 2 coloring can be tested much more efficiently than 3 colorable. Okay. But the algorithm is basically you enumerate all maximal independent set, and for the remaining graph, you test that is 2 colorable now. So you color them with 2 colors and you color them with the 3rd color. Okay. But in 2005, Beagle and Epstein gave an algorithm for 3 coloring that ran in this much time, which still is the fastest known. Okay, so let me talk about some other structure. So other structure that I want to talk about, it's a induced paths. Okay, so what is an induced path? This is an induced path. Okay, so what is an induced path? Induced path means look at this note, there is no edge connecting one vertex to other vertex except those that are in edge. So for example, this is not an induced path, because if you look at this path, look at this vertex and this vertex, there's an edge between them. So this is not an induced path. Okay, so you can ask similar question, how many induced paths can a graph have? And here's a graph with these many induced paths at least. How? So you basically have chain of 3. How many such chain? N by 3. And you make between them complete bipartite graph here. Like between any 2 pairs, there is an edge. So now any induced path will start from here. It can pick something here. It can go from here, here. So basically, you pick one vertex each from each part, and that will correspond to an induced path, right? Because the only edges which are going is from part 1 to part 2, part 2 to part 3, so on and so forth. So everyone we have a 3 choices. There are n by 3 such rows. So 3 to 5. Okay, and we will show very similarly to what we did before, that this is all that we have in a graph. Okay, so what is SARP IP denotes number of induced paths. Okay, so let's say this number denotes induced path in G that starts in U and ends in V. Okay, so what is IP of n? It is maximum number of induced paths which is possible over all n by n plus 2 vertex graph, right? And of course, starting with U and ending at V. Now notice, if you start an induced path at U, right, then you must go to one of its neighbors. But can you come back to its neighbors? Absolutely no, because you go here, then none of its neighbors is possible to be on that induced path. Because if you do something and you come here, then this is not an induced path, because U and this vertex has an edge. Okay, so any induced path has to go to someone in its neighborhood, but never visit anyone in N of U again. So this is a property of an induced path. So now we will use this property to upper bound number of induced paths which are possible in any graph on n vertices. Okay, so again we have such a recurrence. What is IP of n? Is maximum over D here, IP of n minus D. Right? I choose starting at this which vertex. So my induced path either can contain this vertex, and then I forget all this, and in the remaining I find n minus D, or it can contain this vertex, then so that I have D choices for the starting vertex, and given that choices, the problem reduces to n minus D. Okay, and how can you do that? By just deleting all these vertices except this, and in the remaining graph you delete this, and you want to find path starting at this vertex. Okay. And again, like before, you can show that this is at most 3 to the power n over 3. Okay, so you can show that no graph can have more than this many induced paths, and there exist graphs with these many induced paths we have shown, and this is tied up to polynomial factors. Okay, and upper and lower bounds are also known for induced cycles, but we will not talk about that. Okay, so let's have a small recap. The upper bounded what? Maximal independent sets, induced paths and cycles. And but you can ask, is this branching or induction all that we can do, or there are some more clever tricks? So let me give you a different set of trick which is used in this area. Okay, so this is a very classical lemma from combinatorics from 1966, and this is called Bollobás Lemma. So what does it state? So you have an universe U, okay, and these are sets of size P from this universe. And B1 to Bm be sets of size Q again from this universe. And what is the property of this? Such that if you look at this A1 and B1, A2, their intersection is empty. Look, if you look at the pair A1, B1, their intersection is empty. If you look at the pair A2, B2, their intersection is empty. If you look at the pair AM, BM, their intersection is empty. But if you look at intersection of AI with any other set like B2 to BM, or intersection of A2 with B1, B3, and so on and so forth, they intersect. Okay. Now you can ask, U could be anything. Okay. Universe could be anything. And suppose if I put that P is like 2 and Q is like 3, right? A trivial bound seems to be that, oh, I'm asking a question, how many such pairs can you make? So what is the property of this pair? So we have A1, B1, AM, BM, okay? Each of them are of size P, this is of Q, P and Q. So for just to make it concrete, suppose P is 2 and Q is 3. And I'm asking, how many such pairs of sets can you make, right? So, and universe is arbitrary. It could be as large as you can imagine. And it turns out that number of such objects that you can make is at most P plus Q choose P. So it is independent of the universe size, right? It only depends on the size of the sets you can create, P, and the size of sets Q. So if I choose 2 and 3, it is basically 5 choose 2, right? So I'm telling you, you think of any universe of any size, and I ask you, okay, how many pair of 2, 3 size sets can you create such that what is the property? If you look at the pair themselves, they do not intersect. But if I look at AI and intersects with and see its intersection with any other BI, they do intersect, right? So how many such pairs of sets can you create, or how many pair of such sets can you make? This is upper bounded by P plus Q choose P. So in our setting is 5 choose 2. So let's see a proof for this. Okay. So consider a random permutation of the universe. Okay. So it's a random permutation of the universe. And you ask yourself, what is the probability that all of AI, okay, all of AI, so this is a permutation, okay, and you are asking, what is the probability that all of AI occurs before all of BI? Okay. So what is this? So how many permutations are there? In factorial permutations are there. How many permutations are good? So I will do is that first I know P and Q. So first I guess P plus Q choose position. Among them, I know that first P position must belong to A, but they could be in any order. So that's like P factorial. Okay. And then the rest of them belongs to B, and that could be in any order. So that's like Q factorial. And for the remaining elements, I don't care where they are. So if you do this maths, you get this number. Okay. So what is the probability that all of elements of AI occurs before all of elements of BI? So this is a bound. Okay. Now I'm asking, what is the event that all of AI before all of BI and all of AJ before all of BJ are disjoint? Why? Look, here is an AI and BI, they are disjoint. Now, if the same permutation has the property that all of AJ occurs before all of BJ, then how it will be? Right? But you know that BJ has to intersect with AJ, right? And you know that AJ has to intersect with BI. So how these things can happen such that, you know, these are contradictory things. Or in other words, look at this. Here is your permutation, here is your AI first, okay? And here is your BI first. Now you know that all AJ also occurs before BJ on the same permutation, all the AJ, okay? Now look at the last element of AJ, okay? Last element of AJ is, suppose after last element of AI, then every element of BJ is here. It can't intersect. Okay. So if the last element of AJ is before last element of AI is here, then this guy cannot intersect with BI, right? So same permutation cannot support both all AI occurs before BI and all AJ occurs before BJ, which implies that these events are disjoint. Okay. So now what is happening? So I can sum up all these things. So here your universe of n factorial, you know, set of permutation or set of permutations that supports AI before BJ, they are disjoint. It means, And for each of them, the probability is before this is this. So you can sum this up, and this should be less than equal to 1, because after all, this is a probability distribution. And from there, you get a bound that M is at most P plus Q choose P. Okay. So, I mean, there are several proofs, and this is one of the proofs for this fact. And now let me give you an application of this nice combinatorial lemma in something called finding a minimal UV separator in a graph. Okay. So, okay. So what is a minimal UV separator in a graph? G is an inclusion minimal vertex set S. Okay. It's a minimal vertex set S such that U and V belongs to two different components. So if you delete this set S from your graph, U and V gets disconnected and they belong to different connected component. Okay. Okay. Right. So basically, this is what is called separator, something that separates U from V in my graph. Okay. And there's a nice result by Fomin-Willenger from 2008, which showed that any graph has at most these many number of minimal UV separator. And the proof goes as follows. So you consider all minimal UV separators S1 to Sm of size P such that, so look, here's a U, okay? And what I'm looking at all separators of size P, okay? Such that, look at the component Ci of this Si such that U is here, this is the size is Q. Now, by nature of separator, okay, what is the property? That Si and Ci are disjoint. So Si and Ci are disjoint. And Si and Cj will overlap. Why? Let's see. Okay. Here's our U and V. And here's a separator that contains U. And here's a separator that is neighbors of it. And there's a V outside. Okay. Now look at any other separator of exactly same size, right? It cannot, like it starts at U, right? And it contains some vertex that is not here. How can he go? He must go by Si. So every other separator that contain U of the size exactly equal to P intersects with other Si. Okay. So now we can, what we know that by Bollobás lemma, that number of minimal separator is upper bounded by P plus Q choose P. But there's a very nice property, okay, that look at U, okay, and this is P and this is Q, right? So there's also V somewhere, but let's only be interested in counting minimal separators starting at U, because why I want to do that? Because look at either component containing U or component containing V is at most N minus P by 2, right? By induction, by what do you call it? By Peterson-Hall principle, at least one of them has size at most half, right? So suppose Q was like this, then it is 2Q plus P should be less than or equal to N. Okay, but it is possible that for some Q this does not happen, but in that case, I would have counted the separator from the V side and the same property holds. So this is why it is enough to consider P comma Q such that this property holds. So now if you maximize everything, okay, so the number of minimal separators is at most, you sum over P plus Q choose P, but P plus 2Q is at most N, and you get this number. Okay. So, I mean, I do not expect that you will be able to follow everything that I try to say, but I hope that you see that I'm trying to count number of objects in a graph. Okay. Trivial bound is 2 power N, and I'm trying to get an upper bound across all graphs, which is far better than 2 power N. And you're able to see some nice tools being used in this. So first tools was like just recursively branching. Second tool that I told you was about using this nice combinatorial lemma that basically tells you that how many such set pairs can you make. And that set pair theorem has been used crucially in many applications, starting from pure maths to combinatorics to discrete maths to whatnot. Okay, so there is also a version of that theorem. Okay, let me tell you a little bit. node. Okay, no. Okay. Okay, so let me tell you some other, before I tell you algorithmic application. So there's a generalization of that theorem. So suppose you have n some matrix, say n times p plus q matrix. Okay, and now your AIs are spaces of dimension p, and your BIs are spaces of dimension q. And you say that, look, AI intersection Bj as a subspace is empty if and only if I equal to j. And then you ask, how many such pairs of subspaces can you create? Okay. Then there's a proof by Bollobás, using very nice proof by Bollobás, which again says it is p plus q choose p. But there is no known combinatorial proof for this fact. The only known proof is via exterior algebras and those kind of things. So, and together with these two has found lots and lots of applications in algorithms and combinatorics, complexity theory, and all kind of things. Okay. So if you have some interest, please have a look at those theorems. Those are very interesting theorems in itself. So there are some algorithmic applications. Let's just forget it for now. Okay. But we can make this counting to work for some objects called potential maximal clique, and you can get tons and tons of non-trivial exact algorithms for problems like tree width, minimum fill-in, feedback vertex set, blah, blah, blah. Even if you don't know these terms, that's perfectly fine. All I want to tell you that this simple counting paradigm that I showed you, and this way of counting this minimal separator has led to several non-trivial algorithms in literature. Okay. And here's the lower bound on number of minimal separators. Okay. So here's a graph. Okay. ST, and there are n by 3 paths of length 3 each. So now, how many minimal separators are there? Well, you have to pick at least one from again each. Okay. So that means these. You might think that, okay, this guy is always making just these kind of 3 to the power n by 3 separators. Well, there is a paper by Gaspers and McKenzie in 2018 who says actually graphs can have slightly more number of this, but in terms of upper bound, we still know only these. So there's still large gap between the lower bounds that we are able to show and the upper bounds. And but in planar graphs, we can show that the number of maximal independent sets, minimal separators between two vertices is upper bounded by this. And this is tight because the graph which I showed you some time back is actually planar. Okay. See, this is a planar graph because they can be drawn in a plane without any edge crossing. Okay, so one thing which was open for a long time was something called connected dominating set. So S is a dominating set if the closed neighborhood of S is vertex set, and S is connected dominating set if graph induced on S is connected. So S is a minimal connected dominating set if blah, blah, blah. Then it used to be open if there exists any non-trivial bound, like can we show that you have number of connected, minimal connected dominating set is upper bounded by some 2 minus epsilon to the power n. Can we say anything more meaningful than just 2 power n? And it took us a lot of time before we settled down, but epsilon is very bad. It's like some 10 to the at more than 10 to the power minus 50. So it's just a, let's say, I would say, I mean, it's just for the sake that 2 power n is not the right thing. One should try something else. Okay. What they call proof of concept. So let me tell you the last thing that I wanted to tell you. Okay. And this is about minimal de-Heating set. Okay. So let U be universe and F be family, x1 to xm of sets over U. And what is the property? All xi have size at most d. Okay. And we call S is a hitting set if S intersects every xi in F. So what is a hitting set? If S intersects every set xi in F. Now let's ask ourselves, how many minimal D hitting set of size at most k are there? So for any k, there are at most d power k minimal hitting sets of size at most k. How proof? This is very simple. You pick up any xi in family that is not yet hit. Okay. Guess which vertex in xi goes in the hitting set, right? There are d options and budget decreases by 1. So you have the following record. Hitting set on k is at most d times hitting set k minus 1, which leads to d power k. But now notice that for any set S and K, there are at most d power ways to extend S by k vertices to a minimal hitting set. How? So you're given an S and you want to say, can I extend this S to a hitting set? Okay, fine. So what will you do? Basically, you do the same proof. You pick up xi in F, which is not yet hit, and do this. So given any set S, in how many ways can you extend it by k, what you call k elements extra, so that it becomes a hitting set is upper bounded by d power k. So let's define a family R is C uniform if for every S and K, there are at most these many ways to extend S by k vertices to a set in R. Okay, so what is the property? So I'm going to call a family R C uniform if for every set S and element K, how many ways can you extend your S by k vertices to set in R, okay, is upper bounded by the phi power k polynomial. Okay. So, okay, this is what we had, which immediately implied that the family of minimal D hitting sets is D uniform. So you look at all minimal D hitting sets, right? Of course, we're talking about size. Now you take any S, right? And you ask yourself, by how many ways can you get into this by at most in k elements, it's upper bounded by d power k. So that implies that D hitting sets, family of minimal D hitting sets is D uniform. Okay. Remember, a family R is C uniform if for every S and K, how many ways can you extend this by k vertices to set in R? So I told you, you start with this set, you look at the non-hitting set, a set which is not hit, you have d possible ways to extend it, but every time you extend this by one element, your budget drops by 1, so you can only do it d power k. Okay. So now you ask, how many minimal hitting sets can there be as a function of universe N? So we proved this theorem in 2016 that if a family is C uniform, it contains at most 2 minus 1 by phi these many sets. Okay. So how many minimal D hitting sets we will have is 2 minus 1 by D to the power N, because every D, minimal D hitting sets are D uniform. Here's a simple proof. So let R be a C uniform family, and we need to prove that the size of this set is upper bounded by this quantity. So what will we do? So we are going to design a random process, okay, that will output a set S. Okay, so what are we going to design? We are going to design a random process that is going to output a set S, okay, in R. We will prove that for every X in R, the probability that you're going to output S, okay, equal to X is this much. Okay, and then we are done. Right? What does it mean? That every element, for every element of your family, you have a non-negative probability to output that. So overall, the object will be upper bounded by this one. So how many such objects? So think of this way, right? Suppose here is your R, right? And here are points in R. I tell you that, look, I'm going to give you a random process that you pick up any element here, and with probability some alpha, you are going to output it, any element. So now you ask yourself, okay, then how many elements are here? I know that sum of alpha is less than equal to 1, right? So suppose alpha times how many objects are there is less than equal to 1. So How many objects are there? 1 over alpha. So this is how you can show using a random process an upper bound on number of objects in a set. So what are we going to do? We are going to set up a random process that is going to output a sum set S. And we are going to show that, look, you give me any element in your R, I'm going to output this with at least this much probability, right? And this is true about every element. So now you ask yourself, then how many elements are there in that universe or that R? So everyone is like, so total into alpha is less than or equal to 1, because if you sum up the probability, it is upper bounded 1 because it's a probability distribution. But that also allows you to count things. Okay, so let's set up this random process. So our random process is very simple. It picks a random k less than or equal to n. It picks a random t which is less than or equal to k. It picks a random set t of size t, and then it picks a set S from where all x in R, x equal to k, okay, and t is subset of x uniformly at random. Okay, and if none exists, then s equal to 5. So what I'm going to do? So I'm going to pick a k less than or equal to n uniform randomly. Then I'm going to choose a t which is less than or equal to k again randomly. Then I'm going to pick up a set t of size t. Okay, and then I say, look, how many bays can I extend it? Let's choose one of the ways I can extend it uniformly at random. That is what it is. So you look at all x in R, okay, size of x is k, and t is subset of x. So basically what I'm saying that, look at this your R. I don't know how to do this process. I say, look, the sets here has some size from 1 to n. So let me guess that size. So that is what is the first process. So I'm guessing the size of the set which I'm going to enumerate in this process. Now, based on that, I set a small, so basically think of this way, is that this is my sum set in R. I first guess its size. Okay, then I want to guess a small subset inside this. Okay, so to do that, what I do, okay, fine, this is my set. So what is the size t object that I'm going to guess from here? So I first guess the size, and then I guess the set itself here. And then what I say, okay, fine, now among all the sets that can extend, pick one of the sets uniformly at random. Okay, so that is my whole random process. Now let me show to you why this has the property that we are seeking. Okay, and this is the S which you are going to output. So this is analysis. Okay, let x equal to k. This is your set. Let's fix this. Okay, what is the probability that S that you output is equal to x? First of all, what is the probability that you have guessed the correct size is 1 over n, because you are choosing one of the numbers from 1 to n uniformly at random. That's correct. Okay, then I don't know what I'm going to guess t. I could guess t equal to 0 or t equal to k. So based on that, so there are k plus 1 numbers. So you will guess one of these numbers t, right? There are k plus 1 choices, and you choose one of, like you choose t, one of them uniformly at random. So 1 over k plus 1. Now what do you choose then? Then you choose a t. I want to say, if s is going to be x, then the t what I'm going to choose must belong to x. So what is the probability that I choose t subset of x of size exactly equal to t? And then what is the probability that s equal to x, given the fact that x has size k and I have already chosen t? So what happens? So you have x. Okay, this is the probability of guessing its size. It's a probability. This is sum over the probability of guessing the set which is contained inside this, for which I want to do this computation. And this is a probability to guess this set. And what is the probability of, this is a probability of guessing an extension of t. Okay, so now I'm going to do this like I did just 1 over n square, and I just take the max probability of this summation. Okay, like max t less than or equal to k. Now you ask yourself question, what is the probability that t is contained inside x? Okay, so how many good sets are there? Let's look. So out of n choose t sets, that is all sets of size t, how many sets are contained inside my x? K choose t, right? So that's a probability that I will guess a set which is completely contained inside x. So that is k choose t. And given this, how many extensions are there? there are c to the power t minus k extension. So what is the probability that S is, no, so, okay, so this is not right. Okay, we'll see. Okay, so how many extensions are there? So extensions are there are c to the power k minus t. So what is 1 over c to the power k minus t is c power t minus k, right? So this is what this number is. Okay, okay. And now if you do the maths, okay, this is what you get. So if you do some differentials and like this and that, this is what you get. Okay, so what is the general methodology? The general methodology is very simple, that you set up your space where you want to count the objects. Okay, now you set up a random process which is going to output, you output every element of this, and it outputs every element with some good probability, or the probability which is in your head that you want to get an upper bound on. Okay, once you have this, then 1 over that is your upper bound on the size of the set, right? So it's very simple. Imagine that you have a family and I say, hey, look, I know that some of these numbers is 1 and each number is like 1 over 100. So then I ask, then how many numbers you have? Well, then you have at most 100 numbers. That's it. So it is as simple as a computation if you think. But what is non-trivial is setting up a process, a random process, which has an ability to output every set here in the universe which you wanted to bound, and you want to upper bound that with good probability. If I would have been able to say that, well, I'm going to output this element by 1 over 2 power n probability, then you get nothing, right? So you also have to lower bounded probability as good as possible if you want to get an upper bound as good as possible. So there are several, so this is a very general way of counting things via probability. And so that is the last example that I wanted to give. Okay, so here are some remarks. So this analysis is actually tight for C uniform families. So, but this analysis is non-tight for minimal two-hitting set. Why? Because we showed that what is independent sets? If you look at the complement of independent sets, it's like set of vertices which intersect every edge. So those are like minimal two-hitting sets. So we know that there are at most these many minimal two-hitting sets. But what our theorem says is 1 minus 1 by C to the power, 2 minus 1 by C to the power n. So C is 2, so our theorem will tell 1.5 to the power n, but there are C uniform families for which it is tight. So the corollary, we saw that, like Moon in 1971 showed that minimal feedback vertex set in tournaments. What are tournaments? Is basically, you look at a complete graph. What is a complete graph? Between every pair of vertex, there is an edge, and you make an orientation. So these are called tournaments. Okay. And so Gasper and Minich showed in 2013 that this number is between this and this. And as a special case of three-hitting set, this result will show what I just now told. It is upper bounded by this. But later people worked more hard and they have been able to show slightly better bound. So this race was started by Moon, who used very beautiful degree sequence property of tournaments to get this bound. And then a lot of progress has happened over the years to get better and better bound. Okay, so the summary I gave you, like lots of interesting things like maximal independent set, induced paths and cycles, minimal separators on planar graph, is like minimal separators on general graph, D-uniform families, how many such objects are there, and so on and so forth. Okay, so there are, for a lot of these things, there are lower bound, there's an upper bound, and there's still thirst or desire to come up with a bound which is as tight as possible. Okay, so here are some open problems, close the gaps. So also another problem is that in directed graph, there's something called minimal feedback vertex set. All we know is that this is all that they have. So yeah, or you show that maximal 10 colorable induced subgraphs in not directed graph, even in undirected graph. Okay, is these mean? So like you can think of your problem if you're trying to do something and graphs or something and say how many such objects are there in this. Come up with a right definition of those objects and then try to count it, try to enumerate it, and it leads to some very nice and beautiful tricks and techniques. So that's all that I wanted to tell you today. So thank you.
Any questions from the